All right, part of your assignment over the weekend, we talked about this right at the end of class on Friday, but in order to express exact net accumulation as opposed to approximate using interval widths of size delta x, when delta x is extremely small, those approximate net accumulation expressions we can write are fairly accurate, can be as accurate as you want them to be just by making delta x increasingly smaller. But the idea of if you make this smaller and smaller, we get something precise that doesn't change anymore. It doesn't keep alternating into a couple different shapes that we're headed towards something. The idea of what it's headed towards is expressed by notations like this. So this integral notation represents exact net accumulation between a starting value and a general ending value, or it could be a numerical ending value, just like with our net accumulation function's approximate form. We could think about, well, what if I wanted to find the net accumulation between 1 and 1.8? I could also express accumulation from 1 onward to a general x. So this expression here, just to recap, would be representing exact net accumulation from 4 to any general x beyond that, where this rate of change function that causes the accumulation is given by function g. The symbol t is used. T is a variable that we have when we're expressing this, but it's not a part of the original problem. You don't have to know what t represents in terms of a quantity in the problem. What we understand t to be is a variable that ranges from 4 through any value of x. So what we allow this to do then is we let our rate function g have all the independent values of its variable between 4 and whatever we want. And we call the variable that does that t, because I want x to be an independent variable of my accumulation, an independent variable that represents, if I were to substitute in a number, where I'm stopping measuring that accumulation. 4 is where it started. So there's a constant that represents the beginning of the accumulation, and a variable in our formula to represent the end of the accumulation. But of course we can put in a number for that, because you can substitute in values of independent variables into functions. But the independent variable in this expression here as an exact net accumulation function, the independent variable, this would be x. And t is kind of taking on a subset of all the different values that x could potentially have. It's the one from 4 onward. But in any case, I think I talked about most of the pieces in there. Oh, so if I wrote something like, and you saw this, capital G, I was using capital G to be the name of the accumulation function, whereas lowercase g was the rate function, both of those exact. So I've got an exact rate function, lowercase g. If I name my exact net accumulation function, uppercase g, I just named it that. Sometimes that sort of technique is used as lowercase, uppercase, when there's no specific meaning to it, but in any case, I just arbitrarily picked it. So my capital G of x would represent accumulation where x is the independent variable, starting at 4 and going to x. So it's a net amount of accumulation between two values whenever I pick a particular value of x. So capital G of 17 would represent net accumulation between independent variable values of 4 and 17. So 4 was built into the problem. 17 is expressed in the independent variable position. And the rate function that causes the accumulation, again, is this lowercase g. The expression in here is just like our expressions within the summation. It's an MDX sort of expression, a rate times a small change in that variable where we evaluate the rate, a small amount of time passing if you want to imagine it as that. But we choose it incredibly small, essentially 0. It can't be exactly 0 or there wouldn't be any change happening. But to go on to the questions I asked you to look at, we wanted to decide whether each of these did or did not define accumulation function rules in the way that we'd expect them to. So, for instance, this first one is exactly the one we just saw. So it's g of t dt from 4 to x. That's obviously okay. That's the one that I just had up on the previous page. So some of these, like the one next to it, also have just a function name stated here. Some have an example of a function rule stated there, like this middle line has function rules, Actually, all the rest of them do. The top two have functions called by name, and the others have functions named by like just the actual expression of their function rule. And you'll see those either way. You don't have to do anything different when looking at these other than just understand there isn't a function name assigned to this. But let's say that I'm looking at this expression. If I want this to be something where it's expressing net accumulation as a whole, then I would need this part here to be the function rule of a rate function, which, okay, it's a weird rate, 2v minus the natural log of v plus 1, but that's fine. So I have my m dx sort of expression. So far so good. And then I also need to look at what's on the integral sign. That where do I start and where do I end? Because sometimes that can be what throws it off from being not quite what we want to happen or not quite expressing what it seems to be. Because this looks so far, just looking at the integrand, the expression after the integral sign, it looks like, okay, I've got a rate function, right here. So here's a rate of change. And then I've got my differential here. So this is like an m dx. So far, so good. My rate is expressed by a weird formula rule, and I let accumulation occur starting at a. All right, it's a generic a parameter, but that's okay, and going through x. So I can let this, sometimes it's referred to as a dummy variable. It's not that it's meaningless, it's just that it isn't something entirely separate from the other pieces of this. So I let v vary from a to x and take on all the values to express all the different rates between a and x. So this is a well-defined function. This expresses accumulation between a and x. Maybe I'll call it just capital F or something. The independent variable would be x, since that's where the integral ends. And so this way, if I were to substitute in and find capital F of 3, that would mean I'm finding accumulation between a and 3. And here's the function rule that I use. So this is my rate function rule. I've got a differential that has the same variable involved in it. There's v that's in my rate function. So just like m dx, I want to have maybe, if it's actually symbols dx, I would need to have x's in there. If it said dt, I would want to have t's in the rate function and so forth to be expressing changes in the same quantity. But this is a well-defined rate function, as is the first one above here. Now, looking over at this one here, which just has a rate function name, essentially, instead of having a rule written out like what is r sub h of x? I don't know, but I can imagine it's some rate function. But if you see what's the difference between this one and the one to the left of it, there's not enough different symbols used, which seems weird. Like normally we try to eliminate lots of excess variables. But this one here, if I can imagine, I let x vary from -3 to x. Well, that seems a little bit weird. But for instance, what if I called this function, I'm just making up a symbol, q of x. Let's say q of x was this. And then I wanted you to find q of 7. If you wanted to find q of 7, that would mean you'd have to replace x with 7. So I'd find accumulation from -3 through 7. But it's not using a function r sub h of x anymore, though, because it's got an x in it. And we just, by putting this 7 there, would mandate that this is a 7 and this is a 7, meaning I'm not actually using a rate function rule that changes between -3 and 7. I've just said, all right, we're going to use the rate at 7 for this whole interval, -3 through 7. So although it does express accumulation, it's not necessarily exactly what you think it means. So this turns it into a constant rate problem, not a varying rate problem, by having the same variable inside and outside, or inside and on the integral symbol. Because for any particular value of x, the rate then becomes fixed. So if I were to evaluate q of 5, I would be using one particular rate, whatever the rate is at 5, for that whole interval, -3 to 5. Whereas if I were to change if I were to take and change this to some other letter, like I'll just use t. T is used a lot, just like f is used a lot for functions. It's used a lot inside integral function rules like this. Just as it's easy to use, and lots of people use x for independent variables on the actual function. So if I call this q of x, I let t vary from -3 to x. So now if I were to pick and say, oh, what's q of 7, I would be not evaluating r sub h of 7 along the whole way. I'd be using all the different values of this r sub h function that exist between -3 and x, using all the different values of x, but within that interval that ends at x. So just technicalities of writing this. I could say that this second one here, if I fix it a little bit, I could make it an accumulation function that means probably what somebody might have meant if they're looking at this, because if you're going through the difficulty of writing a whole function rule or a whole function name there, we might as well actually use it as a function and not just one of its particular values. All right, so I did want to point out, let's see, this one and this one. Do you see what those two have in common that's different from the other four? Yeah, there's no variable in the integral. Those two don't represent accumulation functions. They represent a particular amount of accumulation. So both of those expressions are actually numerical values, and I could calculate their value using GC, because there's actually also a function rule. So this would be the accumulation between 10 and 15, bottom left one, due to rate function with independent variable a taking on all the values between 10 and 15, a times sine of e to the a, dA. So this mdx is expressed, and I let a take on all the values between 10 and 15 to generate all the different rates that we're using within that interval. And so let me just show you on GC, actually, because although we're not going to be calculating those things for a while, GC can calculate them because it knows a lot of math. Let me clear this off, sorry. So in GC, I have lots of different things on here. If you don't have to memorize all the shortcuts, like integral. All right. So I don't want an integral of 0 to 1. This question was, what, 10 through 15. And so you can just click on here, 10 through 15, and our function was e to the a. And, oh, it's sine of a times e to the a. So it has a number for this. All right. Sine of a times e to the a. Oh, sorry, I forgot to change this. I need to change this to an a, otherwise that's meaningless. There we go. So you could use x's throughout, or in this case, whatever letter throughout, because there's not a variable on the integral sign to have this confused with. So this would represent accumulation between 10 and 15, given the function rule sine of a times e to the a for a rate function, where we let a take on all the values between 10 and 15 and do this mdx, or add up, sum up all the small amounts of change within this interval, given by use each of the values for a little tiny bit, and then add on the next one for a little tiny bit. But this does it all at once. So GC can do these things very quickly. We'll talk about how to actually compute values and closed form, meaning things that just involve like normal functions you've seen, not sums of infinitely small, infinitely many parts. We'll talk about how to do that, but that's kind of the end of the semester. That's obviously something that takes a while, but at this point we can already express it, which is good, because that means with technology we can get results for values of things. We could get results for graphs of things. Like, what if I actually, let me change this to an x. Now it's not a value anymore. Now it's a function, and I could have GC graph this. So this, this is what this function looks like. I didn't write function notation and then retype it as y equals, but I had 10 through 15 before. Now, if I were to zoom into my graph and look what happens between, or what's the value of this by the time I get to 15, it's going to be that, let's see, let me just do this way. All right, and then zoom in. Oops. This is going to be hard to see because of the sign stuff going on. But it, no, doesn't want to do that. But each of these points on here, remember what graphs mean. Each of the points on the graph of this represents, I'm not going to try to get to 15 because that's too hard. Each of the points of the graph on this represents, like that right there, when x is 9.860599, oh, I could go past 10. You can go before 10, by the way. This just means what happened backwards. The amount of accumulation is 0.006743, because this function here, the output of that is an amount of accumulation, what happens due to this rate. So it's a crazy looking graph, but each point on the graph, remember, has an independent and a dependent variable. And it doesn't really matter if I'm past 10 or before 10 or wherever I'm looking on here. No, I'm not going to get there that way. Sorry, I'm going to have to do this the old-fashioned way. Nope, doesn't like me at all. So, come on. But you can see at 10, if you're to zoom in, what do you think the value of this function is at x equal to 10? I can't see a lot, but I'm zoomed out pretty far. If I measure accumulation from 10 through 10, yeah, nothing. Accumulation from 10 through 10, nothing has happened because we haven't had a chance to do anything yet. So if I look just a little bit past 10, and no, it's not going to cooperate with me. If I look just a little bit past 10, I'll see changes away from 0. But if I zoom in very close to 10, I will see that at that value, it equals 0, and it should because of what this means. All right, so enough with playing around with graphs and me not being able to zoom. So we'll get to that in a second, and that. But just, again, looking at, oh, I guess I didn't have quite the right function. You get the idea, however. So in any case, this bottom left one and the middle right, those are both numeric values, an amount of accumulation between the two values that are on the integral sign, the lower and the upper limit, which typically speaking, you'd put the lower number on the lower end and the upper number on the upper end, or the higher number on the higher end. But you can actually play around with that and do other things, something you'll discuss in Calculus 2. But this bottom right function, just to point out, because that's the only one we haven't mentioned at all yet, this is a perfectly nice looking expression, but it has the same problem as the top right one does. Too many uses of the letter t. So just like this one had x's inside and on the integral sign, both as the independent variable of what I assume to be the end of the accumulation, and also for, well, it makes me have one rate throughout. This one does the same, just uses the letter t. So maybe I could change the letter inside, I could change the letter outside. I just don't want those to be the same letter in both places. So if I change this and call it x or something, and it doesn't have to be x with t inside. It can be any two different letters, but we do need two different letters. They play two different roles. One is the actual independent variable of the net accumulation function. The other is this, as I said, it's sometimes called a dummy variable. Doesn't mean it's meaningless. It's just, it is related to, but not the same as, the independent variable. It takes on all of the values between the beginning of the accumulation and the independent variable value chosen, or a general value of x. Here, that is the independent variable spot in our function. So now I could call this something like a sub L of x, or whatever I want to call this. But now it's an independent, it's an accumulation function, exact net accumulation between 0 and x, by making this an x here, where here's my rate. T in this rate function rule takes on all the values between 0 and a general x, or any given value of x that I'd want to put there. All right, so again, the point of all of this is this integral notation expresses exact net accumulation between the number on the bottom and either a number on the top or the independent variable out on the top as a net accumulation function. So let's get on to the other things that we've seen that I said we'd take a look at. All right, this one next. So we're going to do a couple of things with this, but kind of wrap up, putting all of our pieces together. Suppose that here, a tub with a clogged drain let some water through, but just maybe slowly. At time t equals 0, the faucet is turned on. And the graph shows the rate of change of the volume of the water in the tub. The volume of the water in the tub, its rate of change is measured by this. The rate of change is given in gallons per minute. The independent variable of this rate of change function is t, time in minutes, just using the symbol t so we can talk about this easily. So take a couple minutes, think carefully about what's represented in this graph. Think about what are the independent and the dependent variables again. And there are 5 questions down below. But first think about what this rate graph is really showing us. And in fact, you might even want to, as a starting point, I've suggested this to people in office hours. Even though it doesn't say this, when you see graphs or descriptions of what's going on, it might be helpful to draw a graph of your own. Now this one has one graph, but this is a graph of a rate function. Maybe I want to think about, what does the accumulation function look like? What would be the independent and dependent variables of that? Now, one of the parts of this later, I think. You can use the answers to the questions below to kind of fine-tune that graph after, but maybe just think generally about what this would look like. We started out this unit talking about water in a tub, so I figured might as well finish talking about water in a tub. This is a little bit more complex tub here than we started with. All right, so again, in our rate graph that's given, this is the graph of the rate of change of the volume of the water, where the rate's given in gallons per minute, and the time, so as not to have to do weird unit conversion. T is given in minutes. So if I were to not deal with weird unit conversion sorts of things, just take those values as they are, do sorts of normal things, what sort of independent and dependent variables would I have in the associated net accumulation due to this rate? What would be the independent variable? T, time again. Yeah, so T, time, and I'd still be measuring it in minutes unless I wanted to convert it into something else. What would be the units on the dependent variable? Yeah, if I don't do any unit conversions, it's going to be measured in gallons. So gallons per minute used over a period of minutes will give me back gallons. All right, so the first question asks, at what time does the tub have the most water in it? But let's take a step back from that. Let's just look at the rate graph for a minute. If you remember the very first day we talked about bathtubs, because bathtubs and Usain Bolt explain a lot of calculus. Bathtub, we had a horizontal rate graph. I believe it was at a y value of 1.5 dependent variable value, so that was, the water was filling at a rate of 1.5 gallons per minute. We've got a more complex tub situation going on here, but at the beginning of this, near the start of what's shown in this graph, what's going on by having this rate up here? What does this indicate? Near time zero, or if I'm in a moment around time zero, or including time zero, the rate of change is approximately 2 gallons per minute. Meaning, is the tub getting fuller or less full? Fuller, right. This is the rate, so again, reading carefully, shows the rate of change of the volume of the water in the tub. And it says I've turned the faucet on, but it's a positive rate. So I have a volume that has a positive 2 gallons per minute near time zero. So positive 2 as a rate means increasing by 2 gallons per minute, although over the first minute, I wouldn't want to say that in the first minute the volume increased by 2 gallons, because why? Yeah, it's not a constant. It's starting at 2, increasing at 2 gallons per minute, but as time goes on, my rate is becoming smaller and smaller. So by time 1, is water leaking out of the tub, or is the volume of the water growing or shrinking by time 1? It's still growing. How can I tell from this rate graph that the amount of water in the tub is still increasing? It's a positive rate. Oh, so positive rates mean that the amount of water in the tub is still increasing. The volume of water is increasing. So when does, back to this question, when does the tub have the most water in it? Yeah, this spot right here, right? Now that seems weird because that looks like 0, and I've got more before and less after, but keep in mind, this is a rate graph. And we said when the rate is positive, that means the volume is increasing. When the rate is negative, the volume would be decreasing. So if I had water that was increasing, water in the tub, the amount was increasing first and then decreasing later, right here where it says 0, right around then, the volume is kind of staying consistent, about as much water is draining out finally as is being put into the tub. Water's coming in, but it's kind of going out through the drain. Here's kind of our tipping point, where the drain finally starts letting enough water through so that the tub stops getting fuller. Like maybe it's like we put Drano in it, we're waiting for it to work, and finally, about 4.2 minutes in, the water starts to go out faster than it's coming in, which is always a good point in plumbing. So if I were going to sketch a net accumulation graph, I know it's going to be an increasing number of gallons at first and then decreasing after time 4.2, but where would I start from? Just in general, if I'm graphing net accumulation. Yeah, start from 0. So at time 0, the beginning of, this is my A value here. This is when my accumulation begins. I have nothing that's happened yet, but it increases from there and then it decreases. Let's say this is about after 4.2 minutes, just making up a number for it. So at about 4.2 minutes, we stop going uphill and start going downhill. Is it going uphill at a constant rate in a straight line sort of formation? No, uphill here means accumulation. So I am accumulating first around 2, and then it gets lower and lower and lower. So I'm accumulating water in the tub first more quickly and then more slowly. Without doing a whole bunch of approximations, I could at least kind of say, oh, well, first this is going to be a lot of gallons per minute, and then it's going to be fewer gallons per minute, or the ratio of dy to dx or dv to dt. would be larger at the beginning and smaller at the end for the same amount of dt, or whatever I'm looking at, whatever points I pick. The farther I go on, the smaller the ratio is dv to dt, until I get to around 4.2, at which point the water starts decreasing. So however much water was in the tub at the beginning, I don't have that in this picture. I don't know how much there was that was sitting there backed up. All I have is net accumulation, what happened after I turned on the faucet. So that's why we started at 0. So let's see. Question B asks, at what time does the tub have the least amount of water in it? And C asks, is there more or less water at time 7 than when the faucet was, turned on? I don't know where the rest of that sentence went. So by time 7, I was gaining water for the first 4.2 minutes at varying rates, and then the water's draining out of the tub, or we're losing water, the volume's decreasing at various rates. What's the fastest rate at which the water is seemingly leaving the tub, approximately? Or the most negative rate? About, well, it's not even down to -1, negative maybe 0.7 or so. If this was that point, and we actually, there's a function rule given here, but just looking at it, I can see that this isn't down as far even as -1 gallon per minute. So by time 7, the water that we accumulated in the first 4.2 minutes, by time 7, would that all be gone, partially gone, more than all of that is gone? Partially gone, right? We haven't drained for as many minutes or at as fast a rate. I guess there's not enough negatives to compensate for the positives in this rate. Just estimating wise, this is negative rates, but not very negative. And there's positive rates that were more positive and for longer periods of time. So I'm going to guess, we could do numerical calculations, but I'm going to guess that over the next, till time 7, first it was decreasing slowly and then more quickly. By time 7, I don't know, we have some water still left that accumulated in the first 7 minutes, and that amount hasn't all drained out. So do we have more or less water by time 7 than at the beginning? More still. More than at the beginning, but less than at 4.2, right? 4.2 is when there's that maximum amount of water. And we're going to be doing a lot more with this actually after test also, this kind of translating back and forth between what a rate of change graph would look like and an accumulation graph. But you did some of this in your homework, just picking out some kind of key features about positive rates versus negative rates and what those mean. And in this case, even changing from a positive rate to a negative rate means that our accumulation changes from increasing to decreasing at that same location. So that's the graphing sorts of questions where graphing might assist with that. But D and E are asking about writing functions. So D asks, if the rate of change of the water is given by this function r sub v of t, and it's a quadratic function, so this rate, it's not our accumulation, but the rate function, 0.03t squared minus 0.6t plus 2 is the rule for this rate of change function r sub v of t. So suppose I've got that rate and the tub started with 2.5 gallons of water in it, 2.5. We want to write an integral function for the accumulation that gives the net accumulated change in the volume at t minutes after the faucet which is turned on. So let me ask this. If I'm trying to write the accumulated change in the volume at t minutes after the faucet was turned on, is that 2.5 gallons necessary or not necessary? Not necessary. I want to talk about what happened to how the volume changed. So that is, I'm talking about this. I didn't need to have anything about 2.5 gallons to talk about this. So my net accumulated change, which I have a kind of a sketched picture of up here, if I want to express the changes in the volume at t minutes after the faucet was turned on, that's from time 0 through whatever. We have 0 through 7 pictured, but we could talk about 0 through whatever. This accumulated changes in the volume to express it exactly as opposed to approximately, I just need to know what happens between time 0 and whatever number I want. I could put a number here, 7, or I could talk about a function generally, which is what it actually asks for. I'm going to use a different letter because there's all these T's down here already, so I'm just going to use the letter Q. So that means the independent variable, sorry, I didn't leave myself quite enough room here. Independent variable here, a sub v of q. And then all I need to do for my inner part here is express the m dx, the rate times a differential, using something other than the letter q, because I need it to, that whatever symbol I use, to vary between 0 and q. So I could write it just like this. 0.03 t squared, or I could write r sub v of t minus 0.6 t, I'm going to run out of space, plus 2, so sorry that's on 2 lines there, and then dt. And so it's this m dx expression. I put parentheses around it just like you normally do when you've got a long sort of expression you want it all multiplied on. It is multiplication. Sometimes just notation-wise, that the parentheses will be omitted because we're not actually going to end up doing multiplication to do this. But technically speaking, there should be parentheses around a multi-term rate so that all of it gets multiplied onto the differential. But here we go. And again, you don't have to use t here, you don't have to use q there, but you do need 2 different letters. But this would be the net accumulated changes since we turned the faucet on at time 0 due to this rate. And this is as a function. If I wanted to know what happened by time 7, I'd put in a 7 for q. And I could even evaluate that using GC. Yeah? Right, yeah, the instructions here just said write an integral function. It didn't say, you know, I could write integral 0 through q r sub v of t dt, or I could actually write out what the rule is since we have that option in this case. We have the function rule given. So question E asks to write a function, capital V, that gives the total volume in the tub after t minutes. Not the accumulated function, or the accumulated volume at t minutes after the faucet was turned on, but the total volume at t minutes after the faucet was turned on. This is where the 2.5 comes into play. So the difference between the accumulation, net accumulation, or accumulation between 2 points in time, or the net change between 2 points in time, and this total amount, or total accumulation, total volume that we have, some of it accumulated due to a rate, some of it was just there when we started, is the 2.5. So I could write this a couple of ways also. I'm going to clear off the screen so I can have some more space to write here. But I'm going to rewrite function A, just a second. So for part D, a sub v of, and I wrote it in terms of q, was an integral from 0 to q, just the accumulated changes since time 0, due to function r sub v with some other letter than, something other than q. And again, you could write the name of the function there, or the name of the dependent variable of the function actually, r sub v of t, or you could write out the rule since we have it. But for part E, it wants to know the total volume in the tub. So just to use the same symbols as above, I'll use Q for this number of minutes. Oh no, it says the volume in the tub at t minutes after. So it wants me to use T. Okay, so I can do that. I just have to not use T the way I did before. So I want this to be T, and in fact the other one says that also. But if I suddenly realize this, I don't have to change my whole mechanism, but just realize the difference between part D and part E essentially is that 2.5 gallons of water. And it's just a starting value, y initial plus a sum of a whole bunch of MDXs. So the starting amount of water plus what accumulated due to the rate that we knew about. So since I want the dependent variable to be t, I'm going to have this integral from 0 to t and use something other than t inside. So m, whatever letter you want. So m dx, a whole bunch of those summed up. Again, this integral sign represents summation. Y initial plus a whole bunch of MDXs. All of the different rates that exist between time 0 and a general time t due to this rate. And again, r sub v is given by this quadratic function here. So we could graph these on GC. These are actual complete functions. These are done. They're not nice and normal to compute with. Like from our standpoint, these are really tedious to look at. So we're going to learn the rest of the semester kind of how to do some computations to be able to get more normal looking things for those expressions. But these are actually computable forms for computers. Computers can do adding up a whole bunch of rates of change between 0 and t with extremely, essentially zero size intervals. It's not practical for us, so we're going to find some other means to do that, and that's what's coming up after our test. But before the test, just last sort of point of all of this, we had a 4-step process where we worked hard at getting from knowing exact rates to knowing exact accumulations. But there's this other kind of sub-part to that, this not just the net accumulation, but the total value, the total amount, or the total accumulation you'll see sometimes, but this with a starting value other than 0, just how much is there as opposed to how much has this changed since I started watching. So the a sub v of q is this, or a sub v of whatever letter I want it to be, is this part up here. If I wanted to write v of t a different way, I could say it's just 2.5 plus what that accumulation function gave us. I'd have to use a sub v of t in order to have this be v of t. But the difference between total amount or total accumulation and net accumulation is just a starting value. Net accumulation, when we start measuring it, wherever that accumulation begins, it begins at 0 and goes upward or downward from there, dependent value-wise. Total amount of something or total accumulation starts from whatever we're told. It's something that wasn't due to a rate function, so we have to be given that initial information, whether it's initial as in time 0 or initial any time a when we're starting accumulation afterward. All right, so clear this off and go back to this. I think we're done with that one. Yeah, that's enough of that. So, well, let me just point this out. This is what we're going to be talking about after your test. So we wrote things that look like this. We've got a rate function. Said this is an exact net accumulation function. All right. The normal sorts of functions we're used to have things like trig functions, exponents, square roots, exponential expressions, things like that, where you know, like, okay, if you want to evaluate it, it's maybe not easy, but you understand what these expressions mean, what it means to find an exponent or to evaluate an exponent of or a power of an expression, or subtract or add, or even trig functions, which we'll be doing some review of how trig functions work and what they mean too. But these down here have a finite number of calculations involved in evaluating them for any value of the independent variable. One up above has essentially infinitely many computations involved. So these are what we're used to, and we're going to learn how to rewrite some accumulation functions into this form. Not all can be rewritten. There are some that cannot be. So it's important to understand this form of accumulation, what that's called when it's expressed in terms of like whether it's a summation with essentially infinitely many steps, or this, which is expressing it in just a different notation. Those are called open form functions, or an open form expression. This is open form, meaning, all right, I can see what it expresses, but it doesn't really tell me how to do it efficiently. Or it's something that a computer will have a mechanism to do, but I don't necessarily have a way to do that in a finite amount of time. So these open form expressions, don't let that throw you off. Don't let it make you think that we haven't finished something. We have finished. We can write this expression. It's just not necessarily a form of a function that you're used to. So this is open form. It expresses what we've done or what's going on. I've got a rate function. I've got an MDX, and I'm summing up many, many parts of accumulation to get this result. It doesn't necessarily make a nice, easily computable expression, but using math symbols, it tells us what has to happen. In the same way, you got used to at some point in time seeing things like square root of 7, that you're like, well, maybe I can estimate that, but finding a square root of irrational numbers is not something that is just like, oh yeah, I know what that is. Calculators have a way to do that really quickly, but even square roots are something that are, in a sense, they're really an open form computation. Square roots of irrational numbers, or not irrational numbers, non-perfect square numbers. Square roots of irrational numbers are also awful, but just seeing that and having a sense of what it means. A square root of 7 is a number. It's a number that when multiplied by itself gives you 7. This expression here, this integral from a to x of r sub f of t dt, means an amount of accumulation due to this rate between a and any variable x value. So in the same sense, it just kind of tells us what's going on by understanding what the math symbols are. So instead of writing a paragraph to explain what we want, we make another symbol and put it on there and say, here's how that works. So closed form are usually the more elementary expressions, or, I mean, like I said, square roots aren't necessarily simple. You just got used to them a lot earlier. But things that maybe you know how to do or estimate by hand quickly, those sorts of things are usually called closed form expressions. Addition, subtraction, exponents, multiplication, division, square roots, sine and trig functions, exponential values. They're very much easier to use, but the ones up above tell us what's going on. So in any case, don't let yourself think that this integral thing is something that still has to happen. It expresses what happens, just not in an easily necessarily computable way. Same way that like a square root of 11. You probably know that's going to be somewhere between 3 and 4. So at this point, that's an elementary sort of thought process in your head. But to get more precise than that, you'd probably just grab a calculator. It is a numerical expression, not a function sort of expression. But this expresses something just as well as a square root does, that you can translate internally into having more meaning. All right, so test, Wednesday. Make sure you bring a pencil, ID, and have your brain fully stocked and ready to go. Recitation this week. Also, bring your brain with you because you're going to be doing, in addition to other recitation activities, like a 10-minute or so portion of this test, just so you're not rushed in here, that just relates to one topic, your accumulation sums, and understanding the parts of that. All right, I will see you tomorrow, if not before, or Wednesday, if not before.